bonjour à tous. Je suis Guillaume Conchon Kerjan. Je travaille ici avec Justin Salès. Je fais plutôt des graphes aléatoires, des marches aléatoires dessus. Donc je suis très content de pouvoir parler ici, donc je remercie les organisateurs.
Tu peux parler.
D'accord, très bien. Est-ce que c'est bon comme ça? Donc je vais le faire en anglais parce que j'avais prévu un texte en anglais au tableau, mais c'est difficile d'écrire en anglais et de parler en français, je trouve. So the topic today is cutoff phenomenon for random walks on graphs. So I will start by explaining what's a cutoff, because it's something which hasn't been much investigated until past 3 decades, and it's still widely unknown. So we start by a simple problem. It's a nice story of shuffling cards. So you pick a standard deck of 52 cards, and you perform the usual American shuffle or riffle shuffle. I mean, you split your deck of cards into 2 parts, and then you ventilate the cards like this, and you put them back again together. Okay, so you suppose that you know the law of this mixing. It's a random mixing because sometimes you drop 2 cards from the left, sometimes 3 cards from the right. Okay, it's a random process, but you suppose that you know the guy who mixes this. You know how he mixes, so you know what's the distribution of his mixings. And so for this riffle shuffle, it turns out that players and poker players and other players agree about the fact that if you perform less than 7 shuffles, this is a bad mixing. Some parts of the deck of cards are badly mixed, and people can compute in which way it is badly mixed. And if you perform more than 7 shuffles, then this is a good mixing, which means that you don't have to perform 12, 15, 20 shuffles to get a well-mixed deck of cards. So when people discovered this, then they were a little surprised, because they thought, well, it's a rather quick transition. Okay. And so I will give a model for this, a mathematical model for this story. You take a state space omega, which is the set of order rings of the 52 cards. And you take a transition matrix, so the probability to have the deck in order number x and to move it into deck in order y by 1 shuffle is P of xy. And you suppose, moreover, that there is an invariant measure for this Markov chain. And so you suppose that P is irreducible and aperiodic. And so if you say that if you call dt the empirical distribution of your card game after t steps, so what's the law of the random order of the cards after t riffle shuffles, then you know that the total variation distance between dt and pi is going to 0 as t goes to infinity. So the total variation distance, that's a way of comparing those two measures on the sets of orderings of the cards. And you say it's half of the sum over all x's of dt of x minus pi of x, well, in absolute value. So this means when you say that the deck of cards is well mixed, it means that almost every ordering of the cards has a probability close to 1 over 52 factorial to be the current ordering of the deck. And you can draw a picture for this. Yeah, I have just a place for this. So if this is the distance between the empirical distribution of the invariant measure, and this is t, then you start, if you start in a fixed position, you know the position, so you're almost at this total variation distance 1, and this will be decreasing and go and come close to 0. Okay, so it's a simple computation, the fact that it's decreasing, using the fact that this is invariant for p. And okay. So this is decreasing. So what you can define is the epsilon mixing time. That's the first time that the total variation distance goes below the threshold of epsilon. OK, so this is, say this is t mix for 52 because you get 52 cards, OK? But what happens now if n goes to infinity? Well, in fact, for the riffle shuffle in particular, if you increase the number of cards, and for a lot of other shuffling methods for cards, then maybe this will be t mix of, yeah, this will be what happens with 100 cards. And you will get a curve like this for 10,000 cards, and a curve like this for, well, say a billion of cards. And so asymptotically, this is looking like, it looks like there is a gap here. And this is what we call a cutoff. So, yeah. Is it going upstairs? OK. So maybe I have some, or just blue chalk. OK. So this is a cutoff. It means that t max of epsilon divided by t max of epsilon prime is going to 1 as n goes to infinity. OK? If here is epsilon, and so this is epsilon, and say this is epsilon prime. You see that initially, the mixing time for epsilon prime and epsilon are really different. But when n is very large, then it's almost the same time for the mixing. So this is the cutoff. And OK, let's try to get this one done. Good. So are there questions until now? OK. So now let's move on to the important part of, like, serious part of the talk. That was like the card playing part of the talk. I will speak of random walks on sparse homogeneous graphs. So sparse graph means you want a graph which locally looks like a tree. When you look around a vertex, like its neighbors up to distance 10, you don't see any cycle, or you have a very small chance to see a cycle. And homogeneous means that for every vertex, almost every vertex, then what you see around you is like for other vertices. You don't have like some part of the graphs which are really sparse like this with a line, and further away someone which has a lot of neighbors. Okay, like you suppose that the degree distribution is balanced on the graph. So that means you don't have this. Okay. And I will say really, really vague because there are a lot of random graph models which verify those kind of properties. And for those, and I will speak from one in particular, but it's a lot of models verify this. And so Gn is a graph with n vertices, say, and you give P1, Pk positive numbers with a k larger or equal to 3, and the probability that degree of x equals I is Pi, okay? So you suppose that you have a degree distribution with a finite number of possible degrees, and you don't have only people with degree 1 or degree 2. Okay. And so what you do is that for every x in Gn, you pick randomly its degree according to this law. Okay? And then you choose Gn uniformly among all graphs which have these degree distributions. Okay? So there are two levels of randomness, but what is important is that you have a positive proportion of vertices with degrees, say, 1, 2, 3, or 10, if big K is 10. And you take a graph which is like average random among graphs having those degrees. Okay, and what I'm interested in, the main interest on this is xt is a random walk on this graph, okay? So the probability that xt plus 1 is y, if you know that xt is x, it's 1 divided by the degree of x if and only if they are neighbors. Like you get x here, y here, and so here, p of xy, the transition is 1/3. Okay? And I want to, a powerful theorem proven in 2015 by Berestiki and al., 4 people, says that if you define, this random. So again, you can suppose that with high probability, Gn is connected. You can cheat with the degree distribution for having a connected graph or almost connected graph, and so that the random walk on the graph will be aperiodic and irreducible. So you have the convergence of the distribution of xt to the invariant measure, like this, okay? And with the same notations, you will have the mixing time, which will be log n divided by a constant h plus something of order square root of log n. And this is true for every epsilon. So in particular, Tmix of epsilon divided by Tmix of epsilon prime is going to 1, because this term doesn't change anything in the limit, and this is the same. Okay, and so this is the entropy. It's a constant. And now we would like to give a small intuition of how we get this result. Why is there a cutoff, and why the mixing time is of order log n? So the mixing time is of order log n. So why is the mixing in log n over h steps? Because if you pick the vertex x here, and you look at its neighboring vertices, and you can, each time you pick the new degrees of the new vertices, when you look at the graph around x, you pick them at random according to some kind of bias of this law. It's almost this low. On this tree-like, you can compute that you have a small probability of having a tree, of having a cycle. So this is like a tree. And the random walk on the tree is transient. So you have a transient random walk on this tree. So the random walk is escaping by some kind of way to infinity. And since it's transient, there are some edges that you will visit only once. Maybe this edge, when xt crosses this edge, it never comes back here. And so you can cut the walk into independent excursions having the same distribution. Okay? So you have IID excursions with good moments that give you a CLT on good statistics of x. In particular, there is a positive speed for x. So there is almost a CLT. That's why you get this kind of thing. Okay? And you have an average number of neighbors, and you have an average speed to go here. So the number of people you can discover after k steps is some kind of exponential of k with a constant which will be h. So, because you know that you see that you grow exponentially here. So that's why you get a lower bound like this. And the very difficult part is when you start seeing everybody in the graph when growing this tree. That's when you start seeing the cycles. And you have to mix just at this moment. Okay? Because of this growing structure, you have this lower bound in log n, but you want the same upper bound with the same constant in front of log n. It means that when you reach the cycle, the end of Gn, you have to mix very fast at this moment. And that's. And this is due to the fact that the graph, OK, it's really badly said. This graph is an expander graph. That means if I pick 100 vertices, then I've got at least say 10 new neighbors of those vertices which are not into the initial 100 vertices. Like this graph is expanding quickly. So yeah, this radius here is log n over h. Okay. Yeah, I think my time is over. So if you have, I'm sorry for the fact that it's badly explained, but this should explain at least the lower bound, and the fact that again this graph is well expanding means that when you start seeing everybody, you see everybody with a good limit probability, which is the invariant measure, so that the mixing happens suddenly. Okay. Thank you.
Thank you, Guillaume. Are there questions? Peut-être tu peux dire de...
Si tu... sorry, can you put weights to the edges? So have a random walk that is not uniformly among the neighbors, but add random weights?
Yes. In fact, I'm working on a model which is close to this one, but not exactly this one, on which I can put some weights on the transitions. So the transitions won't be like uniform, and in particular, the random walk is not necessarily reversible. Like the matrix P is not self-adjoint. And yeah, again, the fact that it's self-adjoint was only useful in this very last step when you use some spectral properties, like the fact that there is a spectral gap for P, that the first and second, the largest eigenvalues are well are bounded away from each other. And this is still true for some non-reversible transition matrices if you get some other conditions instead. Okay, I can give you precise references where you can.
So similar results should be expected, or?
Yeah, very similar results should be expected.
With a different value of the entropy, or the entropy would remain the same?
No, the entropy is very depending on the distribution pk or the transitions you give. Okay, the idea is you give a finite number of parameters, like the pk's, and then you make a sort of homogeneous graph with those parameters. They should be the degrees or the weights on the edges, and this gives you the value of h. And the fact that it's reversible or not shouldn't really matter. The reversibility is nice for having exact algebraic identities, which can like suddenly solve the end of the mixing, but it shouldn't be necessary.
Okay, I'm afraid we don't have time for more questions, so we'll continue. So let's thank you again.
Thank you.